Okay, so welcome. I just see there's really a straight divide between engineering and mathematics, but I don't say it again. But it's also fun, right? So we could play some football games maybe at some point, even though it's quite imbalanced. Okay, are you ready for a last lecture on optimization basics, so to say? Yeah? Next week we will start with the real stuff on optimal control, or specific topics on optimal control. But as you have noticed, we already mentioned some important topics now already, and this will be particularly true for algorithmic differentiation or for computing derivatives, which is the current chapter. So what we have used already, and which we used without thinking, was this differentiability of functions, and the fact that that Casardi could generate derivatives quite efficiently. Yeah? And now I would like to discuss in a few details how this is done, and how derivatives are computed on a computer. And of course this will be very quick, and if you need more details, the script is a bit longer than what I can say today, but also there are books on computing derivatives. For example, there is a very nice book by Grivank and Walter that I recommend for people that really want to dig deep into derivatives. Okay, so this is chapter 5 on computing derivatives. The basic object that we would like to look at is a function which has some inputs and some outputs, and this function can be called fu, and it's generating some outputs y, and f is a map from Rn to Rnf, f being the output of this function. And a typical computer function is, of course, not just a function like the exponential or the sine or something, but it's a long code. It's a concatenation, so to say, of a lot of commands behind each other. And if you want to really write it down in details, then we could actually first take some intermediate variables, which I just introduced for technical reasons. So I will introduce some variables that I call x1 up to xn. And I define them to be u. This makes my notation a bit easier. And then this computer function could be decomposed into a lot of intermediate operations where I compute new quantities, which I call n plus I plus 1. And they are defined by a command which is indexed here by I, and which takes all the inputs, all the numbers until n plus I as an input. And this I loop for I from 0 to m minus 1. And so this loop will just take some of the already existing quantities, starting with these, and can create a new one. And at the end, I will have a long vector that I call maybe big X, in which consists of all the quantities x1 up to xn, and then all these intermediate things, xn plus 1 up to xn plus m. So this will be the full output of our algorithm. And please note that these things are, these are operations which typically involve not all of the previously known arguments, but only maybe 2 or even 1. Yeah? So they're typically binary or unary operations, and we call these elementary operations. Yeah? And I think we all agree that you can decompose every single computer code into elementary operations which involve maximum 2 elements. And so the idea of I should say that the idea of algorithmic differentiation is to use this structure in a particular way, and to use partial derivatives of these functions and accumulate them in an intelligent way. I call this chapter algorithmic differentiation. And I should say that I fear that this is a political name because most people call it automatic differentiation. And everyone agrees that we should abbreviate it as AD. So the term automatic differentiation seems to win on the popularity level, while a lot of experts like to call it algorithmic differentiation because it's really a differentiation of the algorithm, and the fact that it's automatic is not the only feature of it. I should say that automatic could, in principle, or when you use a tool like Maple or MATLAB Symbolics or Mathematica, they will deliver you automatically derivatives, but they use a principle called symbolic differentiation, which is different than algorithmic differentiation, what I will present now, and which is also the thing that is implemented in Casadi. So maybe this is a bit abstract, isn't it? So maybe I just give a very simple example. It's a simplified version of the example that we have at the end in the script. Maybe I should first say that this is a definition of an intermediate quantity, and then we select some of these quantities with a matrix C, which contains ones and zeros. So we select some of these intermediate quantities and give them as outputs of our function. And so I hope that you agree that with just having some input u, then a chain of operations that defines new intermediate quantities, and then a read-out function that just selects some of these quantities. Cij is 1 or 0. It's a selection matrix, so that this is able to reproduce every function. And I want to give you an example. So f of u could be the sign of x1 and x2 plus x1 times x2. Oh, sorry, this is now already the notation where I identify the first two elements with x element in R2, or this intermediate x. I should have called it u, then it's really more correct. Okay, so this could be a computer code that's the sum of these things, and I could decompose it into the following lines. I could say x1 is equal to u1, x2 is equal to u2. Okay, that's trivial, right? And then x3 is equal to the product of x1 times x2. That's this first line. Then I can compute the sign of this whole thing that I call x4 is equal to the sign of x3. And x5 could then be the sum of x3 plus x4, and y could then be x5. So this would be a computer code in an abstraction that evaluates that function. Do you agree? So it's just one way that's important to note here is that if I have u1 and u2 and I have it here and there, of course, in an efficient evaluation, I would only compute this product once and then reuse it here. Okay, and so now the idea of algorithmic differentiation is to differentiate every line of this code separately. And there are different points of view to look at it. And the one that I find most intuitive works with some form of vectors that I call augmented or enlarged vectors. So I will actually define I mean, every intermediate operation will change only one component. I mean, it will add one component to this, but I could just say the whole memory of what I have produced until this elementary operation, I could give it a name, and I give it the name x tilde I, yeah, and that's defined to be all the components x1 up to xn plus I. Yeah, so that means in particular that x0 tilde is equal to u, yeah, and then x tilde 1 is equal to u, or actually, yeah, all the things that follow, plus xn plus 1, and so on. Yeah? And only the last one, xm, is equal, x tilde m is equal to the full vector that we called x1 up to xn plus m, which we identified with a shorthand x. Okay, so this is just a way to keep everything that's known at a certain step in the algorithm in the memory, and then we could just say, what we do in a computer code could be expressed by some elementary operations that I call phi I tilde, which operate on the whole vector xi tilde, and which generate the new vector xi plus 1 tilde, which is, how does this operation look like? It will just copy everything. It will copy all the components of xi tilde, and it will append the elementary operation with index I to it, which only depends on all these arguments. That's how we have chosen this, right? So it depends on all the arguments that we had until here, and nothing else. So we could now write in another form what would be our function. Our function f of u is given by the selection matrix applied to this phi tilde m minus 1 applied to phi tilde m minus 2 applied to, and at the innermost level we have phi tilde phi tilde of u, and then we close all these brackets. So it's a very large way to think of this function, in particular because these augmented functions just don't do anything. They just add one new component to the memory of this whole thing. So please note that these vectors grow bigger and bigger, and so you just express the fact that everything here acts on something that you had already in a simple way. So now the question is, if you want to differentiate df by du, I might use the total derivative. Yeah? So how would I compute that? I would compute it by having this matrix C, and then here I have the derivative of this, evaluated at the point at which I am, of course, and then the derivative of this. So that's a simple chain rule, and I call these Jacobians, I call them J m minus 1, and I think in the script I have a tilde, so let me keep the tilde. And then I omit the evaluation point, and at the end I have J tilde 0, which is the derivative of these things. So J tilde I is defined to be the partial derivative of d phi tilde I with respect to its input argument, which is x tilde I. Maybe I'm getting very abstract, but we will apply it in a minute. So what is this Jacobian here? How does it look like? I mean, if you look at the function, it will just have a unit matrix at the top, because it doesn't change anything with these variables. But the last line will contain two non-zeros, at maximum two. Could be also only one. Like in this line you have only a unary operation, so for this line you would only have one, but for the others you would have two. And so we see that this is an expression that we could compute, and of course this product of all these Jacobians with each other is a bit redundant because we have all these unit matrices, but nevertheless I like this point of view of looking at the chain rule. So what we do is we apply the chain rule. And of course this is the full Jacobian expression, and I didn't specify how you would compute it, but AD comes in two flavors, so there's first a question and maybe a correction.
What do the stars stand for again?
Okay, the stars are, maybe I should, this is the unit matrix, and what we have here are the partial derivatives of this small function phi I with respect to some of the variables x1 up to d phi I dx, and then we should say n plus I think, to make These are all the variables on which it can depend. But only 2 of these entries will be non-zero, because this elementary operation typically depends only on 2 entries. Okay, so maybe to give an example, what would be here x for the example, just for the example, x4 tilde, yeah? No, sorry, this is nonsense. So what would be x0 tilde? It would be x1 and x2. And x1 tilde would be x1 and x2 and x3. That's actually the result of the first operation. And what would be now phi 0 tilde? It would be the thing that is obtained by just copying x1 and x2. And here you just perform the command, the first of all commands that we perform, namely x1 times x2. So the numbering of the operations here was 0, this is 1, 2, and this is the selection. So only this is actually the for loop. Okay, so this would be a way, and maybe I compute also J0 tilde, which would be a unit matrix here. And here I see, okay, it's interesting, so it's actually x2, and here I have x1. So it's a matrix with these elements. Okay, in this case it's dense. Maybe I go to another example. So two steps later I will have phi 2 tilde, which then copies all the things that I had until then, x1, x2, x3 and x4. And it computes x5, and it computes x5 by just performing this expression, x3 plus x4. Agree? And what would be its Jacobian? It would be J2 tilde, and that is a unit matrix here. And then it depends on x3 and x4 only, which are the last 2 components. So it has a 1 and a 1 here. So that's what I mean by this last row. It's just depending on two of the components, but there are all these other things are 0. And of course, for larger computer functions, this is a unit matrix plus 2 non-zero entries, and the rest is all zeros. Okay, so now the question is, how do we compute derivatives? And in this context, we are usually interested in directional derivatives, and they can be in forward or in reverse mode. And the first mode I want to discuss is the forward mode. Or maybe I just call it forward AD. And the aim is to compute the directional derivative df by du times a direction u dot for some u dot element in Rn. And I call it u dot. Why do I call it u dot? Just to make it different than u. We call these things dot quantities in this field. It has not directly something to do with time derivative, even though one can think of the input being varied with a certain velocity, and then I would be interested in how the output varies, with which velocity the output would vary. Yeah? So what we have here is a directional derivative. And it's actually a directional forward derivative. And if we think of what we had here, we have an expression for this whole thing. So how would we compute it? df by du times u dot can be computed by having all these concatenations of matrices here, j tilde m minus 1, and so on, up to j tilde 0, and that's multiplied with u dot. And so now, please keep in mind that these matrices get larger and larger, so it could be very tedious to multiply all these matrices with each other, even though they're mostly units. But if you see a vector and then a lot of matrices, it's the most efficient way to evaluate that product is actually to first make this product of the matrix with the vector, and then here's the matrix J1 tilde, then make this product, so that's why I put these brackets here, and so on. So at the very end, you will have made all these products here, and you will multiply it with C. And so now I could give an intermediate name to all these quantities, and what I will do is I will call this thing, the result that comes out here, I could call it x tilde dot 1. Yeah, I mean I could call x tilde dot 0 is actually just u dot, and then I call this x tilde dot 1. It has the same dimensions as the corresponding x tilde quantities. And of course, given the fact that these Jacobians have units at the top, they will anyway not modify the first components. So I could just define these x tilde dot I quantities as being x1 dot up to x n plus I dot. So it will consist of single numbers that I just denote by a dot. Okay, and so now one could do a quite tedious work on it, but maybe I just do it for one example here. So what will, for example, happen here? So what is happening? Let's start with this one. So what is j tilde times x0 tilde dot? Yeah, so this is this first product that we need to form. Sorry, I called it u dot, but I should already use this notation here. So it will be, for the example, it will just be x1 dot, x2 dot, and then here it will be x2 times x1 dot plus x1 times x2 dot. Do you agree? And okay, similar things would happen here. So if I multiply this with a vector, so j2 tilde times x2 tilde dot is then just the product x1 dot up to x4 dot. And here I will have now just a copy of these two things. So it's actually x3 dot plus x4 dot. So you see the only non-trivial things are always the ones that happen at the bottom in this notation. But it's still, I find it intuitive to once have this large matrix notation. But what you see is that actually you don't need to do any work on all these entries, you just need to do work on the latest entry. And that translates, interestingly, to a very simple to remember algorithm to compute the forward derivative. If you just look at the original function, I write it actually once again, x1 equals u1, x2 equals u2, because I don't have enough space. x3 equals, what did I have? x1 times x2. x4 equals sine of x3. x4, 5 equals the sum of x3 plus x4. And y is equal to x5. So I could now just add to each line a derivative line, which is just the translation of this with dots. And for the first two, it's of course trivial. But for this one, it's already interesting. So x3 dot is equal, and now what I said here is actually, okay, it's x2 times x1 dot plus x1 times x2 dot. So is this something that you would find logical? Maybe you remember the product rule for the derivatives. I think here the dot, I mean, at least to a physicist, this looks extremely intuitive, this line, to me. Yeah, so it's actually just how the velocities would propagate through this function. And so then x4, what is it? x4 I didn't specify on the map up there, but it's actually we need the derivative of this thing, which is the cosine of x3, right, times x3 dot. And then x5 dot is again quite trivial because it's just x3 dot plus x4 dot, and then y dot is equal to x5 dot. So you see a lot of things are very trivial, but at the end, what we get here, we get y dot equals df du times u dot. So we have computed it with one forward sweep. using only algorithmic components that are very easy to do. And the key is now to observe that if you look at the length of the code, it has the same number of lines. If you look at the number of arithmetic operations that you need to perform in each line, I mean, mostly exactly the same. Sometimes it is a bit more, like here you have a product, and here you have two products and a sum. Yeah? So sometimes it's a bit more, but one can actually show, and that depends on the set of elementary operations, but for most of the sets that we work with, like what I wrote here, and if you look at languages like C, you can actually, maybe I should say that this whole matrix I call JF, just to make it a bit easier. So the cost to compute JF times a directional derivative, U dot, is smaller than 2 times the cost of evaluating the function f itself. So that's a shorthand. And of course, typically it's much smaller, but this is an upper bound. So it's not much more expensive. And this is an important observation because some computer algebra tools, they would expand these functions into trees, and then very quickly you get very much higher complexity in evaluating. But it's not particularly exciting, I should say, because we could also compute this derivative by finite differences, right? So we could perturb in the direction of u dot and then compute a finite difference. So it's not yet as exciting as the backward mode will be. But there's a question.
Does that also hold for computational complexity? Because there might be functions that when you differentiate them, they become a way more nasty thing.
Yes, so you have this example here, you have the sine and the cosine, right? Yeah. It depends really, that's why I say it depends on the set of chosen elementary operations, but the operations that we usually have are not making the derivative significantly more expensive. I mean, multiplications, additions, trigonometric functions, exponentials, and so on, they are all easier. Actually, exponentials are even easier for one simple thing. If you have a line that says, like, for example, x18 is equal to the exponential of x17 in some long line of codes, its derivative would be given by x18 dot is equal to the derivative of this is actually the exponential itself, right? So it's exponential x17 times x17 dot, so that would be the corresponding line. But in this case, you then, and that some tools use that this is actually x18, right? So you don't need to recompute that number, so it's even getting cheaper sometimes. In that case, it's getting cheaper. The cosine is equally expensive as the sine, and usually it's not getting significantly more expensive. But thank you for the question. So it really depends on the chosen set of elementary operations. Okay. So this is an upper bound. It's not necessarily met, and sometimes, as I showed you, it's actually even cheaper. And the main point why we like it, it's accurate to machine precision, which is not the case for finite differentials. So it has a runtime bound, which is different from symbolic differentiation, and it's accurate to machine precision, which is similar to symbolic, but which is better than finite differences. Okay, so that is forward AD in a nutshell. So the idea of forward AD is, I think, quite straight. Yeah.
The elementary operations, they have to be differentiable themselves too, right?
Yes. Yes.
Have the absolute value.
Yeah. That's right. So that's a very good point. So when you have computer functions which are actually not differentiable everywhere, usually they are mostly differentiable, but at some breakpoints they are not, then you get non-smoothness at these points. You, in fact, cannot evaluate the derivative at these points, but at all other points you could. So what the tools typically do is they just freeze the branches in which you are. I mean, absolute value will be differentiable here and differentiable here. And if you're in one branch, you will know what's the derivative and you can apply the chain rule and so on. But of course, you need to know for each elementary operation in which branch it is. And only that you can differentiate then. You see, and if you're at the boundary point, some tools give 0 at these points, which is just not true, but better than not a number. And some other tools would just say this, I cannot evaluate.
So that actually, like using not a number is actually also from a programmatically standpoint quite sensible thing to do.
Yes, exactly. It also helps. That's what it is designed for, not a number. Exactly. You're right. Okay. So this concept of elementary operations and concatenations of functions, I think, is hopefully clear. I explained the forward mode quite quickly, and maybe I just want to mention one thing because it's really fun. It's something I want to share with you because it's surprising. So what you can do in MATLAB is something you cannot do in other languages. You can do it only in languages where you don't have declaration of inputs and outputs. But there, if you have a MATLAB function that's just called f of u, yeah, and you want to compute its derivative using actually forward AD without using it explicitly, is you can perturb your function into a direction, I call it u dot here, with a small value t, and this is something you know from finite differences, right? But the imaginary trick, which I want to explain, so I will not explain finite differences, I assume you know them. But the imaginary trick is something very surprising if you perturb it into an imaginary direction. Yeah, so this is the imaginary unit. And of course, it's a function from Rn, as I said before, to Rnf. Yeah, so it's a real valued function. But you code it in MATLAB, so MATLAB is agnostic about if it's real or complex. Once you call it with a complex number, it will compute all the operations in complex arithmetic. And now you get the function output, which is perturbed by this thing. And now if you take out of this whole thing the imaginary part of this whole thing, and you divide it by t, yeah, then you get something which is interestingly the derivative of df by du times u dot plus something that is order t squared. And that's something you can prove if every elementary operation is analytic. So if you want to try it once, I invite you to do it. And of course, the interesting thing is now, in practice you choose t, or you can choose t to be something like 10 to the minus 100, which is ridiculously small. If you add that to 1, it's 1 again, because it's smaller than the number of digits that you have on the computer. But because you only divide by it, and you only look at the imaginary part, there is no cancellation problem here. So you can actually work with these numbers on a normal double number. And it means that you get this derivative up to machine precision, and it turns out that it's really delivering you the same as this algorithm. Very surprising. I just want you to try it. I found it surprising. Yeah, it's not efficient. It's just a trick. And what is nice about this is you can have your MATLAB function, and you just call it with different inputs. You don't care what is happening in the inside, and usually it works. But sometimes, if you use wrong things, elementary operations, for example, what you should not use is in this case x prime. Prime is transpose in MATLAB, but instead you should use the command transp of x. Why? Because x prime is not only transpose, but for complex numbers it also is transpose conjugate, and this conjugate makes it wrong. Okay, so this is just a very funny way to get machine precision derivatives in MATLAB. Yeah.
Your question, you said that it is not efficient?
No, it's not efficient because you call your function, which was a real function, with complex numbers. So first, let's double the effort already, and at the end, maybe I should say that very often you want to compute not only one directional derivative, but you want to compute several of them. For example, for all unit vectors, in order to recover the whole Jacobian, And then in this case, if you do it for several forward seeds, as we call that, you would actually each time call the whole function with the complex numbers again. So that's inefficient. Much more efficient would be for every sweep, you would just go through these computations again, storing these intermediate derivatives. Okay, yeah. So it's just something for fun. Sometimes people like to use it, and it's, I think, not necessary when you have Casadi installed. Yeah. The really exciting thing about AD is not what I've presented until now. The really exciting thing is the backward mode. And the backward mode is something which is extremely simple to see if we look at this expression of the total Jacobian here. So, as I said, the total Jacobian is df or df by du, which was given by this product of j tilde m minus 1 up to j tilde 0. And now I could also compute a reverse derivative. And this reverse derivative I like to express in the following form. I would just say it's y transpose y bar transpose times j. So the question is, how would I compute that? It's actually, if this is a forward direction derivative, then this is a backward directional derivative. Derivative. So how would I compute this quantity? I would actually say, okay, it's lambda, lambda, that's in the script. So now I will replace it with y bar times c times j tilde m minus 1 up to j tilde 0. And now you see that there is a vector on the left. I should also say with y bar element in R n f. Yeah, so it has the output dimension. That's why I call it y. So here I call it also a bar quantity, just to give it a name. It's not a dot, but it's a bar. And so if you want to evaluate that product, you see here is a vector, here are matrices of larger sizes, so you better first compute that product, yeah, that's a lying vector, and then again this product and so on. So you could also just say j transpose y bar is equal to, and that's the way I like to write it, it's j tilde 0 transpose times j1 tilde transpose, and at the end is j m minus 1 tilde transpose times c transpose times y bar. And the brackets are always here. And then I have the same as before, just the difference is that now I multiply always with a matrix of this form. And of course, it's the transpose of that matrix here. So I just wanted to note that j tilde I is given by a unit matrix, and then some entries here and here. And so these matrices make the vector usually smaller. So you start with this thing, and then you multiply it the other way around. And each operation, maybe I should also say what happens here. It doesn't modify just the last component, yeah? Because some of these modify some intermediate quantities. And if you really do the algebra, maybe I do it for the example, because it's helping us. So what happens, for example, when we have this one, yeah? Just to have an example. So here we will have j tilde 2 transpose is actually given by 1, 1, 1, 1 and 1, 1, 0, 0. Okay. And so what will it take as an input? This command will take in as an input j tilde t2. It will get a bar quantity with an index that corresponds to the output dimension of this whole thing, which is x bar 3. Oh god, now I realize that tilde and bar mix not nicely together, but it's still the bar. Yeah? And so x bar tilde I is corresponding to everything that's a bar quantity up to xn bar, and then it goes up to xn plus I. So they have the same dimensions as these tilde quantities before, but now they are with bars also. So very nasty notation, I see it. But so what you get is a vector x tilde bar 2. And for our example, after the second elementary operation, you have already, where is our example there? You have already 5 components, right? So what this will do is it will get actually x1 bar is equal to, it doesn't modify it, right? x1 bar. So that's what it translates to. x2 bar is not modified either, so it's x2 bar, the identity, but then the other one is x3 bar is actually the old x3 bar plus what we have here, plus 1 times x. And what do we have here? The component is the last component of x3 tilde bar, which is x5 bar. And then the very last line is this. And here we have 1 and x5 bar. Okay, so that sounds strange. So at the beginning we just copy some things, but then we modify 2 things which have no relation. And it turns out that these things correspond to the line that we had, which said x5 is equal to x3 plus x4, right? So that's what it was. And now it modifies x3 and x4 as a function of x bar 5 and x bar 5. So the resulting code is a bit less intuitive, but basically what happens is that, like here, for every line that we had, we just differentiated it, so that's easy. For the reverse mode, for each line, we will actually first transverse them in a reverse order, because our product now starts at the end. Yeah? And then we will, in each line, actually modify possibly 2 quantities. So for this line, we will actually modify x1 bar and x2 bar based on as a function of x3 bar. So these are not bars, but dot quantities. So let me just do it for this example. And I do the complete code. Yeah. So the example is this one. And now I go into the lines from reverse order. So I basically say, what is this line? It says, this line says x5 bar is equal to y bar. Okay, that's easy. Yeah? But now it gets already, sorry, and I should also say that all x1 bar, x2 bar, all the bar quantities x3 bar and x4 bar are set to zeros. So because they need to be initialized with zeros, I will, which corresponds to the fact that they are not selected. Maybe I should make that a bit more explicit in a minute, but I will first write down the algorithm. So then the next line, this one. So maybe I give them numbers 0, 1, and 2. So these are the numbers of these elementary operations. Now comes 2. So for 2, we do the following updates. It's just x3 bar is equal to x3 bar plus 1 times x5 bar. And what I just said before. x4 bar plus 1 times x5 bar. So that's what we just derived. But then I go to the next elementary operation, which is this, the sign. There I had this derivative, but now it's the reverse order. So basically now it's the function constructs x4 from x3. So now I will get actually x3 bar as a function of x4 bar, but it's multiplied with a partial derivative, cosine of x3, and it's added to the value that I might have had for x3 already. Now that's this operation, 1, and then I can do 0, and for 0 I will do the same. I have 2 inputs, 2 partial derivatives here, and so now I will have to modify x1 bar and x2 bar. So I will have x1 bar is equal to x1 bar plus something, and x2 bar is equal to x2 bar plus something. And this something will depend on the partial derivatives and then multiplied by the output, which was x3, right? x3 bar. And the partial derivatives for x1 are actually x2, and for this one it's actually x1. Okay, so now I've computed a lot of quantities, and please note what we did is we just go in one sweep. We had sometimes more lines of code than before, but maximum 2 times. Yeah? But what did we compute? We computed in this case the complete gradient of our function, which in this case is trivial because it has just x1 bar and x2 bar. Sorry, maybe I should just say the last lines would be, of course, u1 bar is equal to x1 bar, and u2 bar is equal to x2 bar. Okay? So this is just the copying operation at the end to select what I wanted to get. So this was the real algorithm. Everything else was just initialization. And the main result is that we get a complete gradient with just one backward sweep in this case. So the cost of this product, which I could call J transpose times U bar, sorry, not U bar, but Y bar, is can be upper bound by something like, and this is a factor that is also a bit fuzzy, but about 3 cost of evaluating F. That's quite remarkable because it's independent of the output of the input dimension in particular. And this is something you couldn't do with finite differences. So I want to give you an example. So why is this remarkable? So example, nf equals 1 and n equals 10, a million, let's say. Yeah? So you have 1 million inputs in a function. It could be a complicated code, and your cost of evaluating this complicated code could be 10, let's say 1 second. Yeah? So it's a very expensive code that takes about a billion operations, costs you about 1 second CPU time. Okay, so if you, cost f equals 1 second. This is the correct way, right? So what would be now the cost to compute the gradient of f with respect to u, which is of course nothing else than J transpose times 1, right? So then you actually set this thing to 1. So what's the cost of it? The cost to compute the complete gradient is smaller than 3 seconds. So that's something you wouldn't get by perturbing the function. So that's the main message, or the main excitement about AD is that you can compute derivatives of functions much cheaper than you could by just calling them multiple times. So if you think of getting this 1 million numbers, which are composed actually in this gradient, you would usually think, okay, I need to perturb my function in each direction, call it a million times, and then I get an idea in which direction it actually goes. But by AD, you can get it with a much shorter cost. So this result is called the cheap gradient result. And that's the main excitement of algorithmic differentiation. Yes?
This kind of looks like the backpropagation algorithm for non-linear classifiers.
Absolutely, yeah. It's the same. CF, I mean, it's not the same. In neural networks, you want to compute the derivative of a very particular function. And if you backpropagate using this, I mean, if you would evaluate the cost function in a neural network as a computer code and you send it to Kazadi and you compute the derivative, then it will do backpropagation automatically. Yeah? So backpropagation is something when you apply it to neural network training. It's exactly the same. Yeah. But the main message is whatever you can evaluate on a computer, as long as you think of it as a thing that's composed of elementary operations, you can differentiate it. And so after the break, I will talk a bit about tools and then about one interpretation that I wanted to share with you, which is a bit advanced, but I think it's good and useful to share it with you. So if you have questions, please ask them after the break. I think we should do a short break until maybe 15 past, and then we start again. Okay, so I would like to continue. And I want to explain how to compute a Hessian, because you remember we had quite often we needed the second derivative of the Lagrangian function, and so how should we compute it and how expensive is it? So this is section 5.3.1. And so if you think of it, what we needed is something like this second derivative of the Lagrangian with respect to the primal variables, right? So that's something we very often need. And that is actually the second derivative of a scalar function, namely of the Lagrangian. Yeah? So we can just specialize, I mean, we could just say define f of u to be the Lagrangian of u, lambda, and mu for fixed values, for fixed lambda and mu. So you just have a scalar function now, yeah? And f is equal to 1. And then we could say, okay, how do we compute the second derivative? And there, of course, the first question is, if you have this beautiful tool of AD, you could, of course, apply it twice in order to, I mean, you produce one code and then you process the same code with the same tool to get the second derivative. And this is indeed possible, you can do it. But you should do it in a smart way. And if you think of forward and backward, there are many options. One would be to do 2 times forward, 2 times backward, or you can do once forward and once backward in different orders. Yeah? And the most popular, and I mean, maybe I should say efficient, I mean, the idea is apply AD twice. Yeah, so that's no problem. But use at least once the reverse mode. So use backward or reverse at least once. And one way is forward over backward, or sometimes it's also called forward over adjoint. Backward is sometimes called reverse. It's sometimes called adjoint, depending on the context. And one way is forward over adjoint. And there you would first generate a code that corresponds to the gradient of this function fu with respect to u. So you generate this by reverse AD or backward AD. This function. And then you define, you say this is just a new function. Maybe I call it, shouldn't use always tilde, right? So maybe I call this f1. And then I call this is f2 of u. And so now the dimension of this is, of course, n. Yeah? If w is element in Rn. So now you have a function which is actually having a square Jacobian. And the square Jacobian is, of course, the Hessian. So now you know that d or df2 by du is equal to the desired Hessian. That's the Hessian of f1. Yeah? And you compute it by forward AD. Why do we use forward? Because the number of inputs and outputs is equal for that function. So now there is no real advantage of using reverse, because reverse has slightly more overhead, possibly, as you remember from this complexity result. And also reverse has a memory issue. So reverse is something that if it has the same cost as forward AD, you would prefer forward AD. Because in reverse you have to store a lot of intermediate quantities, because you go in reverse order through your function. So that's all I wanted to say about the efficient computation of Hessians. And if you think of it, so that this code itself, for at least one of these forward sweeps, will be as expensive as about 3 times the cost of F1, to evaluate this code, F2. And so if you then apply forward AD to it, you need to go through all possible inputs u, which is n, and the cost could be double. So the cost of the Hessian of a function f1 is smaller than 6 times n times the cost of f1 itself. So please note that the Hessian has n squared entries, or n squared half entries, so it's still significantly cheaper than what you could get by calling your function at different points. Yes?
Script actually says
8.
8.
I will correct it, because it's inconsistent. I modified the number. Maybe the history is that in the past I wrote 4 for the backward mode, and then I modified not everything. Maybe I should also just say that this depends really on the tool you use. As I said, the elementary operations different. And so in let's say mathematical textbooks, you usually say it's a factor that's between 2 and 12, depending on what language you use. Yeah, that would be another way to say it. But I like to give some numbers so that people get an idea. But it's maybe also misleading, because numbers suggest accuracy that we don't have. So the second thing I wanted to note is something which has to do with an interpretation of multipliers as bar quantities. And that's something which will pop up later in the context of optimal control. And so I think it's important to see this relationship, because it's a nice one. This is a section I will add to the script. It's not yet in the current version. So I just have the same setting as before. So I have a y equals f u with u element in Rn and y element in Rnf, and intermediate quantities x element in Rn plus m. Yeah, all the intermediate quantities together. And so if you think of the language that we used before, you could also say, how do we get actually this f of u? We get it by selecting among all the x's. I mean, this y, f of u, we get by c times x star of u, where x star of u solves a system. Of course, it solves it in a very simple way, but it solves actually a system that I call g of x and u equals 0. And now I define it with g of x and u being defined as a function which just, and now comes this crucial definition. So I say bu plus h of x minus the unit matrix times x. And I didn't specify what b and h are, so it's actually b is the unit matrix and zeros. It's a matrix that maps the u's to the first component. It's just to make these first trivial statements clear. So it's actually a matrix n plus m cross n, and h of x is the collection of all intermediate operations So it is something that contains a few zeros for the first lines, and then it contains the elementary operations phi 0 up to phi m minus 1. I mean the really small elementary operations which act on the variables that have been known until that point as before. So maybe I should just write down what this g of x and u is in detail. This decomposition is of course okay now. In principle I have defined everything, but let's get an idea in a bit more concrete form. So what it just says, it says here in the first component u1 and then minus x1. That's what comes from here and nothing from here, right? So then it says un minus xn. So these are the first conditions. There is no h, but then there is no u because of these zeros. But then there come these elementary operations. So here it says phi 0 of x1 up to xn minus xn plus 1. And it goes on like that, phi m plus 1. I omit the argument, xn plus m. So you see this is just another way of writing the algorithm. When I say this system should be equal to 0, I could just say this set of equations should be satisfied. You agree? And of course it's trivial to just find a solution. If you fix the u's, you just choose the x1s to match them, and then you choose the xn plus 1 and so on to match these expressions recursively. So that's actually the algorithm that performs the function. So it's extremely trivial to find the solution. That's exactly what our algorithm did from before. It's just another view to the function. So now what do we know about derivatives? So dy by du would be given by c times the derivative of dx star by du, right? And now dx star by du is something we can get from the implicit function theorem, using this fact that it solves this equation system. So it's just c times minus, and here I use gx for the partial derivative times to the minus 1 gu. So that's just implicit function theorem. Very quickly written, but we can actually expand that to make it a bit more explicit. And in order to expand it, we would just say, okay, it's this minus and then the g of x. So what's the Jacobian of g with respect to x? Maybe I need that extra space here. So gx is nothing from the b. It's hx, the Jacobian of h with respect to x, minus a unit matrix, right? So what is g with respect to u? It's just the matrix b, if you look at the function g. So what we get here is hx evaluated at x minus the unit matrix to the minus 1 times b. Okay, and of course I can reorder these things a bit if I like. So I can just put the minus sign inside here. It's just a matrix, but with the minus sign everything should be fine. So I have 1 minus hx of x to the minus 1 times b. Okay, so now in this perspective, what would forward AD do? If you do forward AD, you just summarize these things first. So what you do is actually you get dy by du times u dot. You get it from this formula actually, 1 minus hx of x minus 1b times u dot. Yeah, so that is what we need to evaluate, and this whole thing you will compute and you will call it x dot. So these are the x dots. You can actually show that it's equivalent to the x dots. Please note that h of x is a matrix that has zeros on the diagonal and some entries on the lower diagonal, but nothing on the upper diagonal, because of this effect that it never depends on past data. So if you look at this function h, all these entries are just lower diagonal. Sorry, and then there are all these zeros on the top. Okay. Yeah, no, it's the correct picture is that there's nothing until the first elementary operation, but there's definitely nothing on the diagonal, and then something starts here. So it's mostly 0 everywhere, but some non-zeros here at this bottom part. It doesn't matter if you would go through it. This matrix is easy to invert because it's lower triangular. So one could do the same calculations that we did for this matrix calculus, and one would get that x dot is actually this quantity. And reverse AD from this perspective is just the transpose of that whole thing. I like to use y bar transpose times dy du. So that is what you apply there. So then you would bar transpose times c times this matrix h x of x to the minus 1 times b. Okay. So that is just algebra until now, but I would like to make it a bit more specific. If you have just a scalar function, for a scalar function, this matrix C is equal to some vector A transpose because it selects just one thing. Yeah? So its element in R1 cross n plus m. So it just selects one thing here, and one could choose y equals 1 because I mean there is no need. It's just one number, so you can specify it to be 1. And you would get this, if I have this whole expression, sorry, and I call this whole thing u bar, right? So here I have y bar, which is given by this, sorry, y dot. In the forward AD, I have y dot equals this whole thing. And in the reverse AD, I compute u transpose bar based on these expressions. So I transpose the whole thing, so I say u bar is equal to b transpose I minus hx x to the minus t, minus transposed, times, and now I have this a transpose here, which becomes an a. So I have this interesting equation system here, and what I claim is that this quantity here, this here, we could call x bar. So x bar would be given by just this thing here, namely I minus hx of x to the minus transpose times a in that example. And so a, as I said, is just a shorthand to make sure that we don't forget that this is now a flat vector. And then the u bar would just be obtained by b transpose x bar, which is exactly what we also had at the last lines of our selection. I mean, out of the x bars, we select some in order to make the u bars. But what is this equation? So how can we give some interpretation to that equation? I mean, as I said, it would just, if you invert this matrix, it's easy to invert, and it will end with the same algorithm that we had for reverse AD. But there is another way to interpret that whole thing. And so this whole thing is actually equivalent to, I could just multiply it on the right with this whole thing, right? So I could actually say this is equivalent to A plus, and I put it to the other side, I put an hx minus I, so I revert these things, I switch the sign, I have the transpose here, and I have an x bar here. And I say this whole thing should be equal to 0. So that's an equivalent equation, just moving that to the other side and switching its sign. And so now the question is if that reminds you of some other equation that you have seen somewhere. So I will tell you, maybe after thinking a moment. So what we have here is the derivative of the function g with respect to x, right? So I just want to regard an optimization problem, and then we see that there is some relation. So regard the problem of minimizing over all x in Rn plus m, the objective function, which is A transpose x, subject to the constraint that g of x and u should be equal to 0. So it's actually a parametric optimization problem that depends on u. If you fix u, this whole equation system will have no other point than the one that is resulting from our forward evaluation, because the function g just implicitly fixes every x. So there's no freedom. It's actually a trivial optimization problem. But you could still think of it as an optimization problem, and that's what I want you to do for a moment. But then you could say, okay, what's the Lagrangian of this whole thing? It's depending on x and some lambdas, right? What is it? It's A transpose x plus lambda transpose g of x and u, and you know that the gradient of the Lagrangian with respect to the x variables should be 0 at the solution. And what is this gradient? It's given by this thing, and then here dg dx at x and u transpose times lambda. So that should be equal to 0 at the optimum. The optimum actually is uniquely defined already by the u. But then after you have found the primal optimum for the x, you could also ask what are the multipliers for that problem. It's of course completely trivial because there is no solution, no freedom in that problem, but still you could compute the multipliers just for fun. And then you could even call IPOP with that problem and ask what are the multipliers, and IPOP will spit out the multipliers. What are these multipliers? It's just the same thing, right? So it's here, this Jacobian was just hx of x minus the unit matrix to the power transpose times lambda. So it will be the same as x bar. So the multipliers of these trivial constraints that we had here, they are just defining all the x bars, or they are identical to the x bars. So bar quantities for a scalar, only for scalar function quantities for scalar for nf equals 1 can be interpreted as multipliers. So that's an important relation which I thought I wanted to share with you so that you know about that. Yes?
So is that true for every problem that uses a scalar cost or objective?
Yes, yes, yes.
So if I formulate my problem in a way that I have a scalar objective,
yes,
the multiplier that I get out will always be the bar.
Yes, of course you need to select also what you have as your scalar objective here, and then you could regard it as this optimization problem. So if you select, for example, the last variable only, like we did in our example before, then A would be 0 and 1. And then it gives you the right bar quantities. So sometimes it's actually easier to remember that than the reverse mode. You remember this reverse mode is sometimes tedious to write down, so it might be easier to do it. What I didn't say, but which I should say, and I want to make this remark, what we did here is we did it by hand, and just to get the concept. But of course, in practice, you never do it by hand. You really do it by tools. So you use computer tools, and these tools work in different ways. And there's two big divisions, or one big division line in AD tools, and one is operator overloading, which is, so to say, not producing new code, but just redefines the quantities that you use, a bit like this MATLAB switch from real to complex numbers. So it's the same code, but you just call it with slightly different overloaded operators. Yeah? So this is one approach. The other is source code transformation. So you take, for example, a C code in, it processes it, and it spits out another C code out. That's, of course, particularly useful when you want to do a recursive application of AD, because then you can process that code again and again and again. So I want you to know about it. Operator overloading is one tool versus source code transformation. And if you use an AD tool, you could know about it. In C and Fortran, you very often use these tools, and usually in C++ you use operator overloading. And there are some tools here. I think ADOL-C is one, CPP-AD another one, and I don't remember all names, but one is a classical one. It's called AD4, ADC, and so on are on this side. And also Kazadi is on this side. So Kazadi internally represents, maybe I should say, Kazadi is not really processing C or Fortran code, but it processes Kazadi code, right? So I mean, you need to formulate your things in Kazadi, but once it is inside Kazadi, it applies forward or backward AD, depending on what is cheaper for the question that you ask. And it will internally represent the functions by source code transformation. So if you ask Jacobian of something, then Kazadi will construct a new Kazadi expression which contains the whole Jacobian as one long expression, which then you can recursively differentiate if you want. Yes?
Automatic differentiation has become very popular also in machine learning for neural networks.
Yes.
Is that
yes.
Are they also using these methods? Or?
Yeah, they don't use these tools. I mean, you just do it by hand there.
Okay, so
yeah.
Like Tiano, TensorFlow, these frameworks just have the derivative manually.
I don't know all the tools in machine learning, but if you compute the gradient of a neural network training function, then you do it by backpropagation, and that is basically AD, but hand-coded usually. Okay. So it's not that that people there use a C. I mean, you could, as I said, you could do it in Kazadi, but then, of course, the expressions might be, you want to evaluate it on GPUs and so on, so it's probably better to hand-code it. Mm-hmm. Okay, yeah, so this is the main remarks on software. Maybe on the user side, we just use Kazadi in this course. Feel free to try other tools at some point. So in particular, the ones which are C-based, you can just very quickly and easily use them with using simple C code. Yeah?
Could you maybe explain how Kazadi is interfacing IP-op, for example? Like, what is it outputting? Like some kind of C code, and then IP-op is calling?
No, it's a good question. So the question is how Kazadi calls IP-opt. Maybe the first thing I should say is, in principle in Kazadi, everything is a function. Yeah, so also the call to IP-opt is a function, but in this case, it's an exceptional function because it's not a differentiable function. Yeah, so we don't regard, or in the standard way of dealing with it, you don't think of the output of the IP-opt solve to be differentiable, right? So it's just, but what then Kazadi does is when you pass, when you call IP-opt with all these input and these expressions, it will pass. You define your quantities, but what it really passes to IP-opt, what Kazadi will pass to IP-opt is one function that gives the function, one function that gives the Jacobian of that function, one function that gives the Hessian of the function, and all these functions are generated by Kazadi. You don't see them as a user, and that's making it convenient to use it. While if you would use, and many people do it that way, of course, if you have a C function for your constraints, you could also send them through a tool. So I've just recently read a PhD dissertation by a robotic scientist. He takes some C code generated by his robotic tool, processes it with CPP-AD, generates first and second derivatives by that, and then passes these functions as function pointers to IP-opt. So you can do it also by hand. But what is, of course, nice for a user here is that we just pass the functions themselves, and because Casadi knows that these functions are Casadi expressions that can be differentiated, it will do all the derivatives for you. So what is passed to IP-opt are not C functions actually, but these are functions that are called by or evaluated by Casadi. So whenever IP-opt needs a derivative, Casadi will deliver it. Yeah, so it's not needing actually compiled functions or such things. So so there's no compile step. It's evaluated inside Casadi, but as if it was a function. So it's making the workflow a bit easier, because in the past you would always need to actually generate these functions and then compile them and then pass them to IP-opt. Here you don't. Does it answer your question?
Like you were wondering, like, what's the big difference between YAML and, for example, Casadi?
There the difference is only that YAML is based, I mean, there are some differences, but one is that the YAML is usually based on symbolic differentiation. So it gets difficulties when you have very long expressions. And Casadi is based on AD. That's one of the differences. The other is that in Casadi we allow the use of numerical functions, for example, implicit functions and such things, which are not as simple to differentiate than what I explained here. But for example, if you have a linear matrix solve, I mean, if you think of this thing, so you have x equals a b, so it's solving, this is a MATLAB statement, yeah? So in Casadi you would write x is lin solve a, b, and if a and b are constructed from Casadi expressions, then also x is a Casadi expression. And of course this is not done by using an explicit matrix inversion formula like the determinant with all these very long expressions, but it's actually done by using the implicit function theorem applied to that expression. So I mean, this x, if you want to compute x dot, I mean, it's of course it's simple for the b dot part, right? But it's a bit more complicated when you differentiate with respect to the a dot, and but still it only needs some inverse of a. I can explain it in detail, but I will not. So what is interesting for Casadi, it's numerical functions can be included in this AD workflow, but that's a feature we don't use. And also it uses AD. But apart from that, I can also recommend YAML environment, in particular for convex solvers, it has more interfaces. Okay. Yeah, I think we are ready. I thank you a lot, and next week we will actually start with discrete time optimal control problems. I think we jump over the parameter estimation chapter. So I want to start now. Yeah, with discrete time optimal control. If you still want to rehearse things from optimization, feel free to either consult the script, but also the script of the numerical optimization course, which was given a few semesters before. Thank you, and have a nice Thursday.